So here are the name of the people of the team that designed VOX and PROV, and there are also affiliation. Okay, so in the first part of the talk, I would like to introduce you to VOX, and at the end, it would be a success if I could have given you the key to understand the details of the implementation and design. So first, have a look at the origin of VOX. The idea was to design something based on UV, but better. So we have talked about related algorithm about UV on Monday and this morning, and just for personal survey who had not heard about UV before this event, just by raising your hand. So everyone, so I can keep on and assume that you know about UV. So the design of UV is two or three simple ideas mixed up. The first one is that it's UV based, where UV stands for unbalanced oil and vinegar. So the parameters are a number of equations, a number of variables, and also the order of a field. Then comes the most important ingredients in the building of VOX, for which we have given a name, a small name, which is hat plus. Plus was with a hat on top of it. It's just to remind Jacques Patarin, who has very fond naming variations on schemes. So this particular variation is very simple. You replace some of the structure equation of the original scheme by some complete random equations. That's it. And then comes the last ingredient, which was borrowed from the idea that Hiroki Furue presented to us on Monday, which is QR for quotient rings. And so this transformation is assigned to a parameter that I've named here L, just for expressing, in fact, the degree of extension required by the QR transformation. And I would say for free, we have also, like all, maybe the vast majority of UV-based secret schemes, signature schemes, the ability to compress the secret and public key by generating a seed, for instance, to keep the public key shorter. And same mechanism also applies to the secret key. Okay, so I enter into detail in the key generation. The key generation of VOX, I would present it as like a cooking recipe. You first take a secret UV secret key based on those two parameters, O over L plus V over L, which is the number of variable, and the number of equation which stays O. And I would say the difference between the plain UV is that you have to take an extension field for generating the parameters. And you can note that you can select the value of this parameter between 1 which correspond to do nothing, in fact, and the max value, which is obviously the greatest common divisor of O and V, and every possible divisor is possible. Then comes the hat plus perturbation. In fact, you change the last T equations. You replace, in fact, in UV you have a bunch of zero in the last T equation. Then you replace those square of zero by complete random coefficients. And again, you have you can use T. You can see T as a cursor, measuring, in fact, some of difficulty to or easiness to solve. And when you choose zero, it means that you do nothing. It comes down to the regular UV, and the maximum value you can give to this parameter is, in fact, m, the number of equations. But in this case, it's silly because the system you get is completely random. So there's no more trapdoor, so it's useless. But in fact, it's also difficult for an attacker to. It's difficult for everyone to invert such a system. So the cursor should have a place between those two extreme values, and we'll see how we can set this parameter after. And for the recipe, the last step is to add a mixing of the equation. Since for UA you already have a mixing of the variables, which is the role is played by T. And so for VOX, you have to also to mix the polynomial. So this game comes to average multivariate quadratic system where you hide a central map between two linear mappings, whose role is to hide the secret mapping. And beware, pay attention. In fact, S must have its coefficient into the small field, and T, of course, which is used for the QR transformation, must have its coefficient in the extension. And that's it. With all those steps, you get a VOX public and secret key. And of course, as I mentioned before earlier, you can have for free the compression, which is even slightest efficient with VOX than with the plain UV. Okay. Next is, in fact, the adaptation to VOX, to the inversion of the secret map. Since the secret map is no longer a plain UV secret map, there's a fix to invert the secret map of VOX. The first step is starting like with UV, is just fixing the vinegar variable with a random value that for this talk we call B. Okay, no meaning with this letter. And then when instantiating the vinegar variable with this random value, instead of getting a complete linear system, you get a system that can split into two parts. One part is complete linear, and the small part, derived from the T equation, has still a quadratic part. And it seems natural to solve. The goal is to at least have one solution. But in fact, we solve it in two steps. First step is to solve generically the linear part. And since, so where's, okay. And with great probability, since this part has more variable than equation, it has O variable and O minus T equation. Naturally, the solution can be represented as a affine space of dimension T. And you can get formally the equation of the general solution of this system, where A0, A1, AT has to be determined at this moment. And you express them so with three variables that I name Z1 to ZT. You substitute those expressions, the relationship between the original or the oil variable and the new free variable into the last T equation, and you get what is in fact the main idea of the VOX design. You get a T by T quadratic system. And to my knowledge, it's the first time we are using in cryptography a solver for solving a small quadratic system. So you solve it, that's it, and I can assume that you can solve it because T is small. So up to the typical value are 6, 7, and 8, but up to 9 or 10, it is feasible to solve, to have a genuine algorithm that solve a quadratic system in few variables and few equations. And that's it. You have at least found one solution. Sorry, you concatenate the solution of the square system and the linear system and the vinegar. Sorry, and so you get a general solution of the secret map. Then. We focus now on the algorithm of signature itself. So VOX is like all you familiar an hash and sign paradigm, follow the hash and sign paradigm. So the hash is simply the hash of the message. And the hash sent, in fact, the output of the hash is mapped to the second, the right hand side of the system. You have to inverse. So you apply S, the invert of S. You invert the map, like I said before, until a solution is found. So in fact, since you get a system of a quadratic system of T equation with T variables, there's a distribution of the number of solutions you can get. You can get 0 solution, 1 solution, 2 solution, etc., up to 2 to the T solution. Okay, and here comes some precision about the way it works. The fact that the first linear system has a very high probability to be regular, then you will enter the next step very often. And the fact that the obtained quadratic system you get is very probably regular in some sense. In sense, that that it can follow for resolution. You can follow the you can follow in fact sorry, I will say it otherwise. Here specifically in this part we made not the assumption. We specifically design an algorithm for solving only regular system. But however, any solver would do the trick. On the other hand, choosing a specific algorithm that solves only regular system has two advantages. First, it is deterministic, so it can be immune to timing attacks. It will use the same amount of time every time, and in fact, the compromise you made by avoiding the non-regular occurrence of the system is balanced by the fact that the version using regular system go fast. Okay, and now general consideration to establish the security of the scheme, to set up the parameters. So the first attack, or equivalently the first condition we have to make to be secure is to stand against the MQ general MQ solver of the public questions. So it is well-known tools that would give you the range of parameters that are possible for making a good UV VOX system. Then I enter a category related to the composition of VOX. These attacks I mentioned in this second place are the attacks that you would mount against VOX using a distinguisher of UOV public polynomial. So the fact is that the span of the public polynomial of VOX contains, in fact, a small subset where the hat plus perturbation is cancelled. I mean, it is in fact the span of the first O minus T secret equations. And so the argument is simple. It just say that if you pick at random one equation from the VOX public equation, there's a probability of 1 over Q to the T that this equation does not hold the hat plus perturbation. And the argument follows that in order to mount a distinguishing attack, in order to reveal that the perturbation is cancelled by chance, you need at least 3 equations. I would call, in fact, for instance, the Kipnis-Shamir attack, where you take 2 equations, you compose one with the inverse of the other, you find eventually what you call an eigenspace, and you need at least 3 equations to have a distinguisher to say that those 3 equations belongs to an UV system, and therefore you have removed, in some sort of sense, you have removed the perturbation. But it's if I choose the parameter such that q to the 3t greater than the security level, then I assert that no attacks would work. Those kinds of attacks. Okay. And last but not least, structural attacks. I mean, attacks that would apply specifically to VOX, not only to UV. And I would thank here Hiroki Furue for mentioning in a comment that was, let's say, 2 weeks ago. It's very, very recent. That there exists, for a specific range of parameters, a possibility of an attack. So maybe I could go inside this attack, maybe if you don't mind. Though the argument is that mounting this attack is multiplying each matrix representation of the public polynomial by a vector, and then you get a rectangular matrix by adding all those vectors. And the fact is that if the vector you have chosen is random, then the rank of this matrix is, in fact, this value. It has O, let's say, O colon and O over L plus V over L lines. So since it's random, it should be its rank. And in the very special case that you have chosen a vector which belongs to the secret oil space, then, in fact, the rank of the matrix you get go down to this value. You got the same number of columns, but the rank may go beyond. And if you choose to have T greater than O over L, then you are above this attack. This attack doesn't work anymore. Okay. And last slide about VOX is so maybe how nice is VOX. What I should say is that why is it efficient? It is because, in fact, the field is relatively big, or medium, I would say. And due to the QR transformation, the public key and secret key are small. Due, in fact, to a relatively large T, but efficient solver, we can keep the computation to very low values. They're very competitive. I remark that for instance, I compete with the former presentation, so it's nice. And also, to be honest, so the initial setting of VOX had the drawback I just mentioned before, namely the O here. The O over L was 8 instead of 6, and T was still 6. So we fall into the scope of the attack. And so, namely, we have I have switched. Here we had 6, and here we are. Here before it was 8, and L was before 6. I just switch over L and L to those value, and it seems okay. Okay now. Okay, but still, VOX is new. It's young, so it may times to scrutinize it. So next PROV. So PROV was also proposed as at the NIST competition by the same team, as I told. Is also UV based, and it's there's just one small tweak in the composition of the building of the secret key. You just remove delta equation. That's the only difference from UV and PROV. In fact, there are two more tweaks, or I don't know if I could call them tweaks, but specification, I would say. PROV is salted, and PROV uses also the BUFF tweak. I must say right now that our main objective was to come up with a security proof, but I'm not the guy who went with this security proof. I must cite Brice Minot and Benoît Cogliati, who would be right now working on enhancement of the proof, giving better thresholds and so on. So in a very short description, PROV is just as UV, using Q2 to the 8th as the base ring. So it's contrary to PROV, it's a binary field. And as I said, I will describe in the signature the role of the salt and the tweak, the buff tweak. And of course, the compression, the mechanism for compressing the key is still available for PROV. So the inversion of the secret map works mostly like with UV. The difference is now when you instantiate the vinegar variable, you get an underdetermined system, since you got O variable and O minus delta equation. So in this case, the system has Q to the delta solution. In the event, it is regular. And one fact that was very useful for the proof is that now the signature have a very good distribution, that enables us to make the proofs. Now, using the inversion for the signature, it is still a hash and sign paradigm, but instead of hashing only the message, we hash a hash of the public key, which is the buff tweak, the message, and the salt. And the salt also plays a role into the proof. So this is the reason of the presence of the salt. And also, for the sake of the proof, it is very important that the vinegar is drawn only once for each signature. Vinegar is drawn at random only once, and salt, on the contrary, may be redrawn in the event there's no solution to the problem. But since in fact the probability that this occurs is very low, this is okay. Yeah, I must admit that the maximum number of retries may not be bounded, but fortunately, the probability that this occurs is low. And once again, I will not go into the details of this assertion, but the design of PROV was made specifically with this idea in mind, the property, the PROV, forging a signature, a PROV signature, is deemed to be as much as hard as inverting the system derived from the public key. Okay, and last slide about PROV. I give here also general parameters. So the Q here is a binary. The number of variable and equation is reasonable. Signature is still affordable. I mean, public key and secret key are a bit more higher. Okay, and for the sake of honesty, I don't give here timings because so far we don't have an optimized version. So, but okay, the figures are still acceptable, but it would I would reasonably assume that we can do very much better than what we have actually. So that's it. Here are the let's say references to our schemes, and that ends my presentation. Thank you.